Well, let's consider, for example, that we have a pipe that, can change dimensions. So it's got some area A1 at this end, some area A2 at that end. Okay, now the problem is that if we have a fluid that's coming in that's incompressible, then the amount of stuff going in has to equal the amount of stuff going out. Okay, so stuff in equals stuff out. So in other words, if the pipe is completely full and we squirt like a gallon of water in here, a gallon of water has to come out the other end. Okay, now the problem is that volume. Okay, so if we had a straight pipe, then volume would be some like X times A. So the area of a cylinder times the height of it. So or A times X. Now, what we're interested in is dV dt, the rate of volume in. So that's going to be A dx dt, so A times little v. So big V is volume, little v is the velocity. And so we will call this R, okay, R sub V, and this is the rate of flow. So this is the flow rate. So this is going to be, some volume per second. Okay, so what we can say is the rate of flow is constant. In other words, if our pipe changes area, so we got A1, we got A2, then RV here has to be RV there. So we know that RV is A times V, so that means that A1 V1 equals A2 V2. So that means for the narrower area, it has to go out faster. Okay, and so we call this the continuity equation. Or your book calls it simply the equation of continuity. So this is the continuity equation. So let's do an example of the continuity equation. So let's imagine that we've got a fire hose and we got firemen trying to pour water, onto a fire. So we get the fire hose here. Let's say that the diameter of the fire hose is 5 centimeters. So that means the radius is 2.5 centimeters. And let's say that water is flowing through here at a rate of 15 liters per second. Okay, so I want to know what's the velocity of the water flowing in. Well, we know that RV is going to be A times velocity. So that's going to be pi r squared times velocity. Okay, so velocity will be RV over pi r squared. So 15 liters per second is the same as 15,000 cubic centimeters per second. So that would be 15,000 cubic centimeters per second divided by pi, 2.5 centimeters squared. And so that comes out to be 764 centimeters per second. So in other words, that's 7.64 meters per second. Okay. So we just found out that the water is going in at 7.64 meters per second. Now, the fire hose, it turns out that's a pretty good clip right there. But for the fireman up here standing at this end of it, holding the fire hose, then the fireman would have to be holding the fire hose and just pouring water onto the fire. Okay, well, you don't want to just pour water onto the fire. You want to project the water a long way. So you need a much higher velocity. So let's say that we want this to be coming out at 42.5 meters per second. So if we're coming out at 42.5 meters per second, we have to have a narrower opening here. Okay, so A1V1 has to equal A2V2. So pi R1 squared V1 equals pi R2 squared V2. So the pi's get eaten, and so R2 comes out to be R1 times the square root of V1 over V2. So R2 is going to be equal to R1, which was 2.5 centimeters, square root of V1, 7.64 meters per second, divided by 42.5 meters per second. So R2 comes out to be 1.06 centimeters. So the diameter of the opening here is going to be 2.12 centimeters. Okay, and so that's the nozzle. So you end up putting a nozzle on the end of the fire hose right here, and so that restricts it right there, and that increases the velocity. Now, you don't get something for nothing here. So you get the fireman here. The fireman is holding the fire hose, but the water is coming through here. The pump is pushing the water through, but this is all going same speed until it reaches this point. All of a sudden, it changes speed. You have the same mass going through here and coming out, but at different speed. So that means the momentum, P2, is greater than P1. So that means that you have to change momentum. The momentum changes as it goes through the nozzle, because that's where it starts speeding up. And we know that force equals dp dt. So that means we're applying a force on the water right there. Well, Newton's third law says for every force, there's an equal and opposite to force. So there's a very large force backwards on the fire hose. In fact, these high pressure fire hoses, the fireman drops it, the hose like snakes all over the ground, and it can actually injure people by swinging back and forth because of the force coming out. And for very high flow rates and very high velocity changes, you actually have to have the end of the hose, the nozzle, bolted down to something. Single fireman can't hold it, even two firemen can't hold it. And so you call that a monitor or a water cannon. And so again, all this relates to the equation of continuity and just the basic principles of fluid dynamics.